Hello everyone. Today we have two subjects, roughly speaking. The first one will be a linear symplectic geometry in infinite dimensions. And similar as linear algebra is like if you do that in infinite dimensions, then you get functional analysis. So kind of like it's the marriage of linear symplectic geometry with functional analysis. That will be the first part of the topic, where I also give like a proper definition of what actually a symplectic form is in infinite dimensions. So that's the first part. The second part will be about diffeomorphism groups, and we will see that certain problems arise for diffeomorphism groups. They talk about their conserved quantities, which usually don't exist like as nice conserved quantities as what you would expect for other groups. So that will be the second part. Okay, so let me dive in directly with giving finally a definition and not just examples. That's the symplectic form. So what we do in relatively like large generality, we look at some locally convex vector space, which I denote by V. So we have a locally convex vector space. Yeah, if you don't know locally convex, think of Banach spaces that should be more or less covering, at least for the first part, everything we want to talk about. But we will see that we need also Fréchet spaces when we come to the diffeomorphism groups, at least. So that's the setting, and we'll consider a symplectic form on that. Symplectic form on V is antisymmetric form on a V cross V into real numbers. So it's antisymmetric. And we assume that it's jointly continuous with respect to this original topology that we put on there. And if you remember linear symplectic geometry from your course at the university, you also know that there will be some form of non-degenerate. And there are actually two classes of non-degeneracy here. We assume, and one of them is weak and the other strong. And the non-degeneracy talks about a map, which is usually called omega flat. So that comes from music theory. And the map is a map from V into its dual. It's a topological dual. And what it does is you send a vector. You plug that vector in, say, the first slot of the symplectic form. And what we get is like a map that eats another vector and gives us a real number. So that's the dual. Form it like this map. And the non-degeneracy weakly means that this map is injective. And we say that the symplectic form is strongly non-degenerate if this map is actually bijective. So that's definition, and we will shortly say if you have a weakly non-degenerate form, then we say it's a weakly symplectic, and if it's strong, then we say a strongly symplectic form. So let me discuss some examples. The first one was a symplectic form. That's just assuming we are on a vector space, so there's no dependency of that form on any of the points. But the standard, like one of the examples that we had was V being the space of all one forms, say on a closed surface, and then the symplectic form eats two of these one forms, and what we put down we take the wedge product of them to get a 2 form on the surface, and then we integrate over that. And that form is non-degenerate. Weakly non-degenerate. So what that means is we have to say that if you change, or if you say like for all betas, you get always 0, then alpha has to be 0 as well. And to see that, we can just take beta to be the Hodge dual of alpha, in which case we get omega alpha wedge alpha, which is then the norm of alpha squared over sigma. And so we see that if that's 0 for then also alpha has to be 0.
You know, really, breaking the chalk.
Yeah. What are also already proven, but yeah. No, hopefully, yes, I'm sorry. So it's a weakly non-degenerate, but it's not strongly. Yeah, it's definitely better. So it's not strongly non-degenerate. Since like if you look at that, it's the one forms, and here it's you get some kind of distributional dual. But if you look at this map, what essentially it's you only get like things that you get by pairing with like a smooth one form. So the image of omega flat of the one forms, you can think of that as like the regular dual of V. So like only the smooth part of the dual sitting in all distributional one forms. So already in this like very simple example, we see that yeah, what we get is that the form is only weakly non-degenerate, not strongly degenerate. And we consider here, just to make that precise, we consider the C infinity topology really as like smooth one forms. So that's the first example. And the second example is like somehow the cotangent bundle, but like just in a linear case. So in this case, we have U locally convex vector space, and then we consider V to be a pairing of U and its dual, or the dual elements, and then we on that vector space V, we define a symplectic form. So we have elements x and alpha and y and beta. The x is out of U and alpha and beta are out of U prime. And what we do is we plug the x into the beta to get a real number. And then we want to have that anti-symmetrized. So we take the y and plug it in alpha. And you can check that this one is weakly non-degenerate. The idea is a bit similar here, that we need to find some particular beta such that yeah, that we like that if you set it to 0, then it shows that x is 0. And the way you do that is essentially by Hahn-Banach theorem. You need to have enough.
You give some reasonable example of strongly non-degenerate one.
Yes, so that's it comes there. So it's very weakly non-degenerate that follows by the Hahn-Banach theorem. And if you now look at the map omega flat from U times U prime into a V prime, so that will be U prime times U prime prime. You see already that in general you would not expect it to be surjective because U prime prime is strictly larger than U. But So if and only if, so omega is strongly non-degenerate if and only if u prime or u is reflexive.
It's only bounded and not jointly continuous.
Yeah, okay, like it depends on what kind of topologies you, yes, that's a good point. So we see that it's kind of special that we have like a strongly non-degenerate space. In particular, you need always, your space you always need to be isomorphic to its dual. So that means that we essentially can only have like a Banach spaces. For example, Fréchet spaces, they are never isomorphic to the topological dual. So in that case, we are essentially always in the weak category. We almost never in the strong category. So it's rather special to have something in the strong. And that's maybe as like the moral of like the first moral slogan is that just as morally is that everything works for strongly. Symplectic forms. Essentially as infinite dimensions. That's like a rough slogan. It's not like totally true. Sometimes you do have like things that don't work for strongly symplectic forms that you would expect from finite dimensions. But usually if you have a strong symplectic form, there's a high chance that the statements that you use from finite dimension works. The problem is almost never you have like like strongly symplectic forms. So it's a bit like.
But would having beta y minus alpha x be also like admissible, or I understand it would be different, but
What do you mean?
like instead of beta x minus alpha y, for example, could I also have like beta y minus alpha x, and it would like.
You do want to have them antisymmetric. So that's like one of the requirements is that it's antisymmetric in these slots. So if I change x and y and beta and alpha, I should get minus the original result. And that's kind of like you want to pair them, and then the sign is kind of focused from like this antisymmetric case. Of course, you can also probably cook up like some other symplectic forms made out of these data, but that's in some way the canonical one that you consider. So yeah, the moral story is that strongly symplectic forms are nice, but we always never have them. So it's and if you look back at like the theory, like most results were actually proven already in the 70s and 80s. They were considering strongly symplectic forms and then did like Banach theory for them and said that's very nice. But like the problem is that in examples you don't have them. So like the nice theory that you already developed back then just does not work. And like in some way, like the symplectic function analysis that I will present today is giving you some kind of hints what you can do still and like how you can circumvent these problems. One of the other issues, even like if you have like strongly symplectic forms, is related to the Hamiltonian vector fields. The next step, we want to talk about the dynamics. It's the Hamiltonian vector fields. And we have already seen, it's like too much to assume that the Hamiltonian vector fields are defined all of our V, of our symplectic form. So that was, for example, in the wave equation, what you saw is that the Hamiltonian was defined on all of the V, but the vector field needed like higher derivatives, so it was only defined on a subset. So in general, what we consider is a map defined on some subspace, and we consider that as a linear vector field called Hamiltonian if they exist one function node which is defined on the same subspace.
V times V. Domain is not a V times V.
No,
No, the domain is really on the subspace of the symplectic
linear case.
And you consider that as kind of like a vector field, but then in the linear world. So the projection on the first factor, so we trivialize the tangent bundle, and then you get like the second component. And we say that this one is called Hamiltonian. If we have a Hamiltonian function, which is a smooth, or it's C1 at least, function also defined on some subset, such that we have omega flat of the vector field. That gives you, by the definition of omega flat, a one form, and you want to have that one form, or the dual element, to be the differential of the function. And the different way to write this is, of course, if you plug in this vector field into omega, what you get is E of H. So first, a few observation is that not every function gives rise to a Hamiltonian vector field. In finite dimensions, it's we have every function, we have an associated flow to that of the Hamiltonian vector field. But since omega flat might be non-surjective, means that we might find like a function such that if you take the d of that, it's not lying in the image of that omega flat. So we can't find a vector field corresponding to these kind of functions. And one remark about the domains. What we have seen already in the wave function is that even if H is defined on all of V, then the domain of the vector field is usually still like not all of V. So that was what we've seen in the wave function, wave equation.
Even if
Can I ask you something? Omega flat goes from V to V prime, right?
Yes.
But X is a map from D to V. I don't understand how do you apply omega?
Yes, so if I plug in Q. So if I plug in Q, which is living in the domain, then I get an element in V. I plug that into the symplectic form to get something in the dual, and that should be the differential at that point Q. And of course, we could discuss now in which sense it's one in one of the many different differential calculuses that you have once you go to locally convex spaces, but I don't want to start that. The second kind of problems that are related to that not every function has a Hamiltonian vector field is related to the Poisson bracket. That's the next step is that if you have f and g, two functions, here this one is defined on d of f, and this one is defined on d of g, and the Poisson bracket of these ones should be a function again, but it's only it's a function which is defined on the intersection of both of these domains, and it's defined by.
You mean d of f is the domain on which the Hamiltonian vector fields exist, probably?
Yes, so by assumption, I assume always that my Hamiltonian function then also
Is the same.
Yes. But you're right, because the way we define it is that maybe I should have said that in this case we write x as x of h, Hamiltonian vector field corresponding to, and so we take our two functions, we assume that they have Hamiltonian vector fields x, f, and xg, and then we plug them both in the symplectic form to get a number, and that number is denoted by the Poisson bracket. And what you already see is, like, first of all, there's like this problem with the domains, but you also really need, for this definition to make sense, you really need a Hamiltonian vector field of f and g. So we really need this assumption that these functions have Hamiltonian vector fields. So for all functions. Because we need like that they have Hamiltonian vector fields. So that's also very different to the finite dimensions, and it's also like the difference between the strongly and the weakly degenerate case. Poisson brackets are mostly important. Okay, like if you're a physicist, they are mostly important because they give you conserved quantities. So let me write that down. And the statement is that if you have your Hamiltonian with like a Hamiltonian vector field defined on, say, dh, and similarly you have function f with Hamiltonian vector field which is defined on df, and we assume that actually they are defined on the same set, like they all have the same domain D, both of them. And we also assume that this Hamiltonian vector field has a zero flow denoted by the flow of h d, and we assume that this flow is defined on D. So everything is like defined on the same domain. And zero flow here means that the natural map from R times D to D is continuous. And we have the following equation, that d of dt of f times the flow of h equals to Poisson bracket h under the domain D. So formally speaking, that equation follows by taking just like the chain rule and then using the definition. So formally speaking, it's relatively straightforward. You have to work a little bit to actually show that this one is a nice C1 function, so you can actually take the derivatives and get what you want expect. And for that, we use actually that you have a nice formula for the floor in terms of the symplectic form. So yeah, so that's one of the statements. And like, yeah, I want to maybe a word of warning is that these domains are really, really important. So you might get like the impression that like all of that discussion with the Hamiltonian vector fields, okay, they are only defined on some subspace, okay, whatever. But it's important that we consider these domains and keep track of them and like have like careful statements what happens if they might have not the same domains, because like essentially a theorem like this might be wrong if they have different domains on which they're defined and the floor of one of them doesn't leave the domain of the other one invariant. So that's somehow, there's two phenomena like in operator theory which are like related to that. The first one, if you have like only a symmetric operator which is not self-adjoint, then the energy is not conserved. There's kind of like energy leaving the boundaries. So that's like why, like one aspect why we need the domain, and it's like important what the boundary conditions are. The second one is that there's like examples of operators, like unbounded operators, which have like a zero, like a commutator, but their flows or like the semi-groups that they induce, they still don't commutate. And that's like something that you don't want. Like essentially, you can think of the Poisson bracket as the commutator. So even if that's zero, then you would say like f is conserved along the floor of here, of this one. But this one is just like in some ways like the commutator. And that doesn't give you enough information if you don't think about the domains, what happens with like the conserved quantities. So it's really important, and you actually can construct counterexamples if the flows are not defined on the same domains and or at least preserved by them.
So you're saying the domain intersect is not true on the intersection of the domains? Not restrict?
You really want that your flow is kind of a map on D, so it needs to map D to itself. So you don't want that like the domain of one of the Hamiltonian is like moved to like over time to a different domain, then you get problems. So of course, if you have like two big D's and you can restrict it and like the flow gives you a nice flow on that smaller D and everything works out, and then it's fine, and then you can of course intersect them. But the problem is that you don't want that the flow of one of the observables is moving the flow of the other one. Like these needs to be in here. So that's just like about the dynamics in this linear picture. And what I would like to discuss now is something that is called symplectic topologies. So the problem is why we look at like different kind of topologies is essentially this distinction between weakly and strongly non-degenerate forms, which says that the weak ones are the ones that we encounter, but the strong ones is like what we want. So the idea about symplectic topologies is that we change our topologies that we look at to make our symplectic form strongly non-degenerate. So the idea is that definition is that a topology, locally convex topology on V is called symplectic topology. Topology if omega flat into the dual. But the dual this time, we don't take the original topology for the to say what the dual is, but we take this topology of the we look at, like we change the topology on V, so and say that this map needs to be surjective. So we kind of fix the problem that our form is not strongly degenerate by kind of just changing the topology on V. So that means equivalently every tau continuous functional alpha on V is of the form alpha of V equals to x of V for V, and that x is then unique by weakly non-degeneracy. So this idea of these symplectic topologies comes from something that is called the dual pair, which is a general notion that if you have a vector space and some kind of pairing, then you can consider a certain range of topologies that are given by this dual pair. And that's like things that we do in functional analysis quite often. If you have like, you can, for example, take like the dual pair that is given by the vector space and its topological dual, and then you get like weak topologies and all of that kind of stuff. And that's like morally speaking, it's the same kind of structure, that you first start with some kind of duality, and then from that you get like a certain kind of topologies. And it's the same thing, except that the pairing is now given by the symplectic form.
Is complete or not?
No.
No. By assumption, it's always a locally convex topology. So then, you know a little bit of these dual pair theories. They give you immediately some structure or some results for these symplectic topologies. So who has already seen like these dual pairs in generality? Who is familiar with?
Different
Yes.
moment maps, so I'm not sure.
In functional analysis, just?
Yes, sure.
Okay, good. But not too many people. So.
There is a book by Fröhlicher and Kriegel from 1988,
Okay.
which base differential calculus on dual pairs.
Okay, in this sense of just like the abstract duality pairing.
Yeah.
Okay.
Convenience basis and
Analysis, I'm sure people use it all the time, but they don't call it like this.
I think it's called officially, at least like by Schwartz and the kind of functional analysis books, they at least call it officially a dual pair. But
Goethe, yeah.
yes, Goethe.
Huge book of Goethe.
So just as a summary, there is something called the Macquer-Arens theorem, which applies to every dual pair, and we can apply it, of course, to the symplectic form, which gives you some kind of an upper limit and a lower limit for these topologies. The lower limit is essentially something that is the weak topology, and then the upper limit is a bit harder to describe, and it's called the Mackey topology. So you actually really know kind of all the topologies, and you can say when the topology.
Some compact subsets of the dual.
The Mackey topology. Exactly. So that's the first statement, and the second one is that the original topology is a symplectic topology if and only if the symplectic form is strongly non-degenerate. That essentially follows from the definition, but it gives you a different way to think about this like problem of weakly symplectic forms, which says like we just have a different topology now to play with. And like originally the problem was somehow completely algebraic, and now we changed like perspective and we get like topology coming in. So in some ways, like looking at like what you said yesterday, is that topology never helped you and algebra never helped you. Here is something like where both of them are coming together and help each other. And one example where you can see that is the following, that if you have U and V, some subset or subspace, then we can form symplectic orthogonal. So the symplectic orthogonal for all vectors out of V such that you plug in, if you pair it with something in the subspace U, you get 0. So that's the symplectic orthogonal, and then you can do that twice. And in finite dimensions, you count essentially dimensions and show that this one is like, again, your subspace. In this case, it's no longer true, but you get a completion of U, and the completion turns out to be exactly with respect to one of these symplectic topologies. Yes. So yes, yes, it's the closure of the U with respect to one of the two symplectic topologies, and it doesn't matter which one of them you take, because they essentially have the same kind of linear function. Also linear subspaces have the same closure, not completion. Yes, and that's something called bipolar theorem. That, so one application where like it's relatively immediate now from this topological viewpoint is, for example, that every finite dimensional subspace has this property that they are the same. Just because they are automatically closed, regardless of what kind of topology I put on there. So that's, you can also show that by hand using algebraic operations, but it's very nice actually to just use topology to solve these kind of problems. And a kind of surprising fact that comes out of this discussion is the following. How much time do I still have? The following proposition. heavy, weakly, properly weak, weakly symplectic vector space as a subspace which is closed to which satisfies that if you take 2 times of the symplectic dual, you get the whole subspace. These are things that we can think of as symplectically dense. So that's something that is very strange if you see that for the first time, that you have a proper subspace, some proper subspace that if you take 2 times of the symplectic dual, you get like all of the space. Actually, there was, if you go back to one of the papers of Marston and Weinstein, where they do symplectic reduction, they kind of assume that they have a symplectic form which lives a priori between weakly and strongly, namely it has this property that if you take 2 times of the symplectic dual, you get always the subspace back. But this proposition shows that like once you have that, then you're automatically strong. So like this class of symplectic spaces that they consider is automatically like the strong symplectic for spaces. Yes.
So this symplectic dual being the kernel in a sense of the symplectic form, is that the definition of the symplectic dual? Or it's in a sense a proposition that describes it?
No, so this one is the definition.
Okay. So it's not a dual space.
No, it's what is called the symplectic orthogonal. Okay. So if I say dual, then that was my fault. So it's the orthogonal. So it's like in the Riemannian case where you have like actually instead of antisymmetric, a symmetric pairing, then this definition is just taking the orthogonal part. But now it's a bit more complicated, or like some of the things that you get from Riemannian geometry are no longer true, or as expected, because you have this antisymmetric pairing instead of symmetric, like orthogonality with respect to the symplectic form.
In examples, you may be lucky, and if you do reduction, for instance, and perhaps you have a subspace such that it's symplectic the orthogonalis itself. It's not like, there exists one that's not good, but perhaps the one that you are interested in doing as well.
Yes. So that's something that we discuss tomorrow. Is like if you do a symplectic reduction, you need to assume that property where U is the infinitesimal orbit. Otherwise, you don't get the symplectic form downstairs. That's essentially what comes down. So I can say like
in the Weinstein paper, how did they formulate it? Was it for every subspace that
they consider essentially symplectic forms that live like that have these properties that it's like every time you get like the form back.
Closed here means with respect to the original topology.
Exactly. So that's like the thing.
Not
like
with respect to tau.
No, with respect to tau, that's not possible because then you would get just U back. But the problem is really that it's the close with respect to the original topology, but like it's symplectically dense, so dense with respect to the symplectic topology. And just to give you an example where that these ones are not pathological things, but so you could, for example, consider U to be the space of one forms. In this example that I had before of the pairing of one forms with one forms, and we just assume that alpha vanishes on a given tangent vector. So x is a given tangent vector at some point. And then you consider all alphas that vanish if you pair it with that. If you calculate that with respect to the integral, then the integral just doesn't see this condition, and what you get is that the symplectic orthogonal double of that one gives you all one forms. And tomorrow I will actually discuss one of the problems where we have these kind of things where the action of the whole group would be kind of like not free, and then you would like to fix, like, but it's finite dimension, then you fix like pointed gauge transformations. And in this case, you actually have that the orbit is of this kind of form. So yeah, like sometimes you're right, like sometimes we are lucky and we get like a nice closed thing. But yeah, like in some examples where I actually want to do reduction, this property is like a bit annoying. Now we come to something that is the taboo theorem, which in finite dimension says that if you have a symplectic form that depends on some point x, and that gives you still a symplectic form, then you can essentially remove the dependency of x if that's like closed. Make it constant. And in the infinite dimension, that's wrong. And there's a nice paper by Marston from, I think, 72, where he gives like a concrete example of like a symplectic form. And the symplectic form has the following structure, that at some point, say at like 0, the omega 0 is strongly non-degenerate. So at some point it's strongly non-degenerate, but we have the problem that like the invertible linear operators are no longer open in the subset of all operators. So what we can do is like we can construct an example where it's strongly non-degenerate at one point, but like outside of that one point, it's only weakly non-degenerate. So all of here, omega x weakly.
It also fails in balance setting?
Yes. So that's it's
I remember seeing a proof that
No, he says it's not in the Banach setting.
like, I think it's even in the Hilbert setting, where like the example is like living in the Hilbert setting. But the thing is, the taboo theorem holds if you assume that all of them are strongly non-degenerate. But you need to assume that all of them are strongly non-degenerate. And that example is saying that like at some point it's not strongly non-degenerate, but then outside it's not strongly non-degenerate. And by construction, you can never find like make it in constant because yeah, like at some point it's strongly non-degenerate. At other points it's weakly, like properly weakly non-degenerate, so you can't make it constant. I have a conjecture, but which is actually a conjecture which is like in that paper just like slightly reformulated or make more precise. And the conjecture says that if the symplectic topology is induced by omega x and omega y at different points are equivalent, then we can apply the Taboo theorem or like construct Taboo and say that it's, we can make it constant. So that like conjecture definitely rules out counterexample of that type because the symplectic topologies are able to detect if something is strongly non-degenerate and some other points weakly non-degenerate. So the conjecture would be like if you have two symplectic topologies at different points and you can show that these symplectic topologies are equivalent, then we can actually get the result of Darboux to make it flat and constant. That,
Only non-degenerate everywhere, then Darboux theorem is true.
yes.
But what if it's nowhere strongly non-degenerate?
Then-
We don't have these like patches.
You mean like if I have an example? Like I don't know if I have an example where it's everywhere, like only weakly non-degenerate, and we still don't know if like Darboux holds or not, or like actually know that it not holds. Like the counterexample that I know is of that form, where it's at some point it's strongly non-degenerate, everywhere else is not, and that gives you. But I could imagine that you have counterexamples where you actually, like maybe something maybe like, for example, you have the co-dimension of that changes, and then at some point it's one dimension, and then it jumps down to 2 dimensions, so it's never subjective, but like it has different kind of flavors of how much of subjectivity you get from the musical isomorphism. But, yeah.
It seems this thing doesn't seem possible in Banach spaces because invertible operators are open.
Yes, I was also, when you asked that, if that's, but
So of course in locally convex spaces you can find
I think that was like, the problem is what exactly do you assume from your map if it's like, if your symplectic form is like continuous as a map from X into if you assume that this one is your symplectic form, depending on a point, is continuous as a map of that form, then of course, but I think like that counterexample was that it's not continuous in this way, but it's you have like V, and then but it's only continuous in this way, even with V, like Banach spaces or Hilbert spaces. So it's like a question if that associated map is then continuous, and I think that's not the case in this counterexample.
But the base point is moving also in a Banach space.
Yes.
the upper line is equivalent to the lower line only if you put on LVV the topology of uniform convergence on compact subsets.
Yes.
But if you take the norm topology up, then these two are not equivalent.
If you would have like something that is like continuous in this sense and like strongly at one point, then it would be also in the neighborhood. But if it's only continuous in this sense, then it might still blow up or like has different. Okay. We still have 5 minutes. Do you want to ask questions for 5 minutes, or should I still?
Or do we get a quick break?
Yes.
Would you give us a reference for this counterexample?
This counterexample is, I think it's by Marston. I'm pretty sure that it's from 1972. And I think it's like a counterexample to the Darboux theorem in infinite dimensions or Banach or something like. It has exactly the words that you expect, and it's a nice paper from like a few pages. And the construction, we can see that it's essentially a it's essentially saying that he constructs a certain metric, or like if you have a metric that depends on a point, then you can identify the, you can use that to define a symplectic form. If you do that, then you get like a certain dependency, also certain derivatives in the coefficients of the metric. And if you choose the metric in a nice enough way, or a bad enough way for that example, then the things blow up. So that's like the idea that it's like, yeah. And then I think he constructs it on L2 or something, like even on a sequence basis. Like the construction essentially works wherever you want to have it work. Right.
I mean, for Darboux, in this strongest sense, you also need the Banach space to have a good basis. So it's
What do you mean with a good basis?
like a Hilbert space, like a
Other basis, probably.
Schauder basis. There are Banach spaces without Schauder basis,
Yes.
and then you don't know how to write it as d of something, which d of.
Yes, that's true. So if you want like have really Darboux coordinates, then of course you need some kind of basis. But you the Darboux theorem in the sense of asking yourself if you have like a family of symplectic forms that depend on a point, can I make it constant if it's like closed? That doesn't make sense regardless of basis and these kind of questions.
More questions?
I still would like to ask about this equation, as you said, it doesn't make sense when the domains are different. So if you have, for example, sequence spaces, then I will assume that if you take as f projection on one of the coordinates, and it's defined on a whole thing, and the Hamiltonian vector field for it is defined everywhere. So you never have an equation like this for the coordinates? That would suggest there is some non-local phenomenon going on.
I mean, like if that's like your Hamiltonian, say, or
Yeah, no, F is a coordinate projection, and you have some Hamiltonian which is not defined whole sequence space. So you cannot use this condition there.
I mean, in that case, I can do because like the domain of F is like even bigger than the domain of my Hamiltonian, right?
But you said you need to be the same. And
Yes, but like that example that you described, I can just restrict F to the domain of the Hamiltonian, right?
But in general, it will not be preserved by the flow.
Ah, that's what you.
Just
But
So the main example that you have in mind is the one parameter subgroup of unitary operators on Hilbert space generated by an unbounded skew Hermitian operator, or Hermitian operator if you put the I in. Then
you have some operator that commutes with that one, but you don't have like a conversation.
there's an example.
Yes. So that's like if you assume bounded operators, then that's
An example due to Nelson.
That's it.
yes.
I think sorry, Thomas, I think he was saying this is just a sufficient condition. Maybe there are more technical things.
Actually, I would be very interested in, like, I think that result is going back, like, I think by now 40 years or so. Like, where they have, like, the same domain, but, like, yeah, sometimes you might have, like, things with different domains. If you have, like, some results there, I would like to see them. That makes more sense in more general context. Like the idea, what I wanted to show here is really that you just can't ignore these questions of the domains, and they also show up in the Poisson bracket. And what is like sometimes in physics, what you see is just like they calculate the Poisson bracket, say 0, and then it's conserved. I just wanted to warn that might not be enough. You really need to worry about the domains if you want to have like a rigorous statement about these kind of things, and not like just formal things. And I was wondering if like the talk about Francois last week, where he also showed essentially if the Poisson brackets might even depend on the boundary, you might get like very strange things. And I was wondering if that's actually, if you can push the boundaries then in the domain, and that would make more sense. So might be a visual thinking.
I think those are, or I can hear the bells again, so maybe we can thank Tobias again.